Alright, section 7.2, just following up on 7.1, was on graphing. 7.2 is on solving exponential equations, and that generally means using algebra instead of graphs. So that is what we'll do today. So how do you solve these equations? Before we actually do this, let's just do a real simple one. Suppose I gave you this equation. I said x plus 2 equals 7 plus 2. Solve for x. Now you could add 7 and 2, or you could notice something. Since these numbers are the same, that must mean these numbers here have to be the same. So that means x equals 7. If these are equivalent, there's a 2 on both sides, and there's a 7 on the right side, so that means there would have to be a 7 on the left. So that principle we just used is exactly what we're going to do to solve these equations. What we always want to do is we always want this number, the base, to be the same on both sides. So the question is, can I take the number 8 and somehow make it a power of 2? And the answer is yes. 8 is equal to 2 to the third power. So 2 to the third is this right here. And then remember, we still have that whole thing being raised to the third power. So that other 3 right here needs to be there. Okay, I don't want to confuse people. The 8 is this thing, and the 3 is coming from that 3 right there. I changed 8 into 2 to the third, and that red 3 right there is still where you see it. So this is going to become 2 to the x equals, and then the rules for exponents are that we multiply those, so that's 2 to the 9th. Well, if 2 to the x equals 2 to the 9th, that has to mean that this and this are equivalent. There's no other way to get those to equal each other, so x is equal to 9. Same thing over here, we want the same base on both sides, so I have a base of 3 right here, and I always take the smaller base and I try to change the bigger one into that. How can I express 9 as a power of 3? Well, 9 is the same as 3 to the second power. And then I still need that other exponent there. I still need this 2x minus 1, so I'm going to put that right here. What should I do with these? I'm supposed to multiply them. So 2 times 2x minus 1 would be 4x minus 2. And that equals 3 to the 6x. So 3 to the 4x minus 2 equals 3 to the 6x. That must mean that this thing and this thing are equal. So let's set them equal to each other, and we'll solve that for x. We'll subtract 4x from both sides. We get negative 2 equals 2x, divide that by 2, and we get x is equal to negative 1. You could always check by taking negative 1 and plugging it in here, and plugging it in here, and you will get the same result in both cases. Alright, let's do one more of these. Let's do the one on the right, 5 to the 5x. So obviously I must be able to change this number into a power of 5, and it turns out to be 5 to the third power. And then I still have to have this thing on the outside, x plus 2. And I'm going to multiply these together. So 5 to the 5x. 3 times x plus 2, you have to distribute the 3 to both of these. 3 times x plus 2 is 3x plus 6. So that means this thing and this thing are equivalent to each other. So let's set them equal. That means 5x is equal to 3x plus 6. We'll subtract 3x from both sides, and we'll get 2x equals 6. So after dividing by 2, we get x is equal to 3 as our final result, and there it is. Alright. This is kind of an example of when you would use this in an actual, there's a lot of science context where you use this. So it says, Kristen starts an experiment with that many bacteria cells after 4 hours, or 23,000 cells. Here's the general form of an exponential function. We talk about it in 7.1. This number is the initial amount. So A stands for the initial amount, that's 7,500. B is the growth factor. Well, obviously we're growing here because we're going from 7,500 to 23,000, so B must be greater than 1. We don't know what it is yet, so we'll have to leave it. We do know that X stands for time, and time is 4 hours. And then Y is the current amount, and the current amount is 23,000, so we can plug in 23,000 for Y. Actually label that for you. Current amount is Y, initial amount is A, and this stands for time. And this is the growth or decay factor, depending. Obviously in this case it's growth because the bacteria are getting a bigger number. Okay, so what we need to do is we need to find B. How can we do that? Well, the first thing we need to do is divide this by 7,500, and the same over here. So we get b to the fourth equals whatever this number is. That's going to be 230 over 75, which is 46 over 15. That's like 3.06 or something like that. So how do you do this? Well, you need to cancel out the fourth power there, and you do that by taking the fourth root. We need to take the fourth root of that number. How do you do that on a calculator? It's not obvious because it's usually not on the main page. Let me show you how to do that. You go to the main page, you press 4 because we're trying to take the fourth root, and then you go to math, and then this number right here, 5, that's the x root, and we told it we want to take the fourth root, and we're getting, the number was 46 over 15. Oops, see if I can type this correctly. So fourth root, 46 divided by 15, that was the 23,000 number that we simplified. So 1.323, and it's usually a good idea to have 2 or 3 decimal places. So b is equal to this right here, and that is growth because that number is bigger than 1. So our equation would be this. Our equation would be, we have to have a y in it, and we have to have an x in it. This number is what we started with, and this number is the growth factor. Okay, so there's our equation. Second part says after 12 hours how much will be in it. Well, we just take 12 and we plug that in for x. So let's do that right now. And just to get an accurate answer, we still have this unrounded number. So I'm just going to raise that to the 12th power. And then that's b to the 12th. That's this thing right here being raised to the 12th power. And then I'm going to multiply it by 7,500. It's better to not round things too early. So if you want to avoid rounding things too early, like let's say I want to store that number, I can hit STO, that button that just lit up, and then alpha, and then store it as a letter, like the letter A. And now every time I press alpha A, it brings up that number. So it's a good idea to store exponents when you're doing those. So 216,302 bacteria after 12 hours. Okay, that's how fast those things grow. And that's generally what's true with exponentials. Okay, here's the kind of the most practical example of when you'd use this. This is money, compound interest. Money grows exponentially, which is kind of nice. And unfortunately, debts also grow at that rate too. If you have a lot of credit card debt, it's not a good idea because it's going to grow exponentially. But here's the formula for compound interest. This number is the original amount. P stands for the principal. R is the rate it's growing. N is the number of times they compound it. So for example, if you get it compounded monthly, n would be 12 because there's 12 months in a year. So monthly would mean n equals 12. If you get compounded daily, well, there's 365 days in a year, so n would be 365. And this number, n times t, is the number of times compounded, and t stands for time in years. So for example, if you put your money in for 3 years, it would be 3, and it was compounded monthly, it would be 3 times 12. Because 12 times a year times 3 years, that would be 36 times that you would get it compounded. Okay, and then, yeah, one thing to mention is not to forget to change percents into decimals. There's a good acronym a friend of mine uses called Free Dr. Pepper. Free stands for, F stands for fractions, that stands for decimals, and P stands for percents. It just reminds you which way to move. So if I have 50%, I don't remember, am I supposed to move it left or right? Well, we remember the acronym Free Dr. Pepper. Percent to decimal means move this way. So I would take 50 and I'd move the decimal to the left, vice versa. If I had 0.5 decimal and I want to change to a percent, well, decimal to percent goes to the right. So move it to the right or to the left 2 places like you see there. Alright, so an investment account pays 4.2 annual interest, so that's R. And we want to change that by making it into a decimal. Compounded monthly, so that means n is 12 because there's 12 months in a year. This number is the initial amount, so that's P, and then this is the time. So let's plug in all those numbers. So P is how much we started with, $2,500. 1 plus the rate is 0.042 over the number of compounding, that's monthly, and then times 12 times 15. So just to simplify that, that's going to be 2,500 times this number right here. 12 times 15, I believe, is 180. So let's see how much money after 15 years. And 4.2% is a decent return. It's not great, but it'll be interesting. We started with $2,500. Let's see how much we finish with. So 1 plus 0.042 divided by 12 times a year compounded, and then we're raising it to the 180th power because that's 12 times a year times 15 years. So almost $5,000, $4,688.86. So that's quite a bit of growth. Given, I mean, you almost doubled your money in 15 years. You started with 2,500, so that shows you how quickly things grow. All right, last thing I want to show you is how to solve inequalities, and they're done almost the same way as equations. Again, we want the same base here, so those are both powers of 2. So let's change 16 into 2 to the 4th power. And then we still have this thing right here, 2x minus 3. And that's less than 8 is 2 to the 3rd power. So let's simplify this. If we distribute the 4, we would get 2 to the 4 times 2x is 8x, and 4 times minus 3 is 12. We have 2 to the 3. So that means this number must be less than that number, because that's an inequality. So we need to not set it equal, but make it less than. So we'll add 12 to both sides. We would get 8x is less than 15. Divide by 8, and we would get x is less than 15 over 8. And we can test that out by plugging in any number that's less than 15 over 8, and it should give us something which is true. And I think it would if you tested it. All right, let me show you one more with that. So we'll do the one on the right here. So we need these to be powers of 2. 32 is a power of 2. That's 2 to the 5th power, but we want it to be on top. So you might remember if we have a negative exponent, we flip it to the bottom. Well, that means if we have a positive exponent, we can flip it and make it negative just like that. So sorry, that's not supposed to be a 25. I know that's what it looks like. It's a 2 to the 5th power right there. Okay, so that is greater than 2 to the negative 5. That means this must be greater than negative 5. So that's exactly what we will solve for. And right here we get x is greater than negative 7. And that should be our answer, and it is. That's just called set builder notation, so a different way of writing x greater than negative 7. All right, last thing I want to show you is we kind of did 1 and 2 on the last page. That would be 2 to the negative 6th power, and that would be 2 to the 3rd power. You do it the same way. Last thing I want to show you is this last problem down here. How do you write a function for a graph given 2 points? So let's just look at this one right here. Here's our function. Here's our normal function. We just take these numbers and plug them in. So I'm going to plug in 5 for y. I'm going to plug in 0 for x. So a times b to the 0. Anything to the 0 is 1. So we just solve for a. We know that a equals 5. So that is part of what we need. We also need to find what b equals. So how do we do that? Well, to find b, we'll use this other point right here. So we'll plug in 3125 for y, because this is a y coordinate. And we already found a. In the last part, we found that a is 5. We don't know b. We do know x is 4 when y is 3125. So we'll divide this by 5. We get 625 equals b to the 4th. Then we take the 4th root of that, which we did earlier on the calculator, and the 4th root of 625 is 5. So b is equal to 5. So our final equation should look like this. Final equation should be 5 times 5 to the x power, and that's exponential growth. And you can probably tell because as x is going from 0 to 4, y is getting much bigger. And so there's the answer. This one right here will also be growth. It's a little bit trickier because there's decimals here, but we'll try the same way. And if you want to shortcut this, you might have noticed something. This number right here, 5, that is always going to be the a value, because when you plug in 0 for x, this whole thing goes to 1. So we can shortcut this by just taking the number that y equals when x is equal to 0. So here's x equals 0. This number is going to be our a value. Okay, if you don't believe that, take 0, plug it in for x, plug 3/4 in for y, you're going to get a is equal to 3/4. So that's just a shortcut for us. And it's a good idea to put the b in parentheses just so we don't confuse calculators if we end up plugging that in later. Here's our second coordinate. Y is 36.75. And b we don't know, but we know that x is equal to 2. So let's divide this by 3/4. Dividing by 3/4 is like multiplying by 4/3. And I believe when you do that, 3 divided, that's 12.2. I think this whole thing is 49. Pretty sure that's 49. 49 is b squared. If we square root 49, we would get b is equal to 7. Okay, so that is our second function. Let's double check. And it is 0.75. They just use 0.75 instead of 3/4, but it's the same thing. So that is section 7.2 on how to solve exponential equations.